What if, time isn't continuous? What if there's a smallest moment, a final frame, where time itself becomes like a silent heartbeat of the universe, whispered in a slow, calming rhythm, fade-in sound of space ambience, stars drifting, then ease into. Tonight, we gently unravel this idea. Quantum time, the smallest building block of reality's clock. Chapter 1. What is time, really? Let's start with a simple question. What is time? We talk about it every day. We measure it. We race against it. We wait for it to pass. But few of us ever stop to ask what it actually is. One moment follows another, second by second, minute by minute. But is time really flowing? Or is it just how we experience change? Time feels like something we move through, like walking across a room. In science, there have been many ways to think about time. His theory of relativity changed everything. He showed that time and space aren't separates, they're woven together in something called space-time. And this space-time isn't fixed. It bends, stretches, and warps depending on gravity and motion. That means time can move faster or slower, depending on where you are or how fast you're going. A long time ago, Isaac Newton believed that time was absolute. To him, time ticked forward like a perfect clock, always the same, everywhere in the universe. Time was separate from everything else, like pixels on a screen or grains of sand in an hourglass. Maybe time is built from indivisible pieces. Stop at the right point, and you realize this isn't a smooth scene. It's a sequence of still images, moving fast enough to trick your eyes. Maybe there's a smallest possible moment, beyond which nothing can be divided. GPS satellites, for example, orbit Earth, high above us. Time is rhythm. We remember yesterday. We look forward to tomorrow. We listen to a song. We breathe in patterns. We sleep and wake in cycles. Our bodies and minds are built around time. They move quickly and experience weaker gravity. Because of this, time actually ticks faster for them than it does for us on the ground. Can time exist in absolute stillness, in complete nothingness? Just a way to organize events, something the brain invents to make sense of cause and effect. Scientists call this the Planck era, a time so small, so brief, that our current physics breaks down. During this moment, the universe was smaller than an atom. Everything we know, light, gravity, space, was tangled together. But asking them opens the door to new possibilities, new ways of thinking about time that go beyond minutes and hours. Time itself may have been flickering, unstable, not yet formed. Is time smooth, or is it built from tiny, invisible steps? And we'll begin to see how quantum physics reshapes everything we thought we knew about time. Is it a real thing, or just something we've made up to tell the story of the universe? Some physicists believe that time isn't fundamental, that it's not something the universe has, but something that emerges when certain conditions are met. Like temperature. A cup of tea has a temperature, but an individual molecule doesn't. You need lots of molecules interacting to get heat. Maybe time is like that. Too, you need motion, change, interaction, to get something like past and future. Let's come back to how we experience time, not as scientists, but as humans. Without adjusting for this difference, your location on Google Maps would be completely off. In the quantum world, energy isn't smooth. It comes in chunks called quanta. Light, matter, even 4 sizzle of them, are made up of tiny, indivisible pieces. So if everything else in the universe is quantized, why not time? A background stage in which the universe played out its story. But that idea didn't last forever. Just like a movie plays smoothly frame by frame, we imagine time as an unbroken stream. No skips, no gaps. But what if that's not true? In the early 1900s, Albert Einstein came along with a new way of thinking. To us, this sounds strange, but it's real. So, time isn't so simple after all. Still, even with Einstein's theory, we treat time like a smooth path, something that flows continuously. What if time has a smallest unit, a limit, a point where time stops being smooth and becomes something else entirely? That brings us to an idea at the edge of modern physics: quantum time. We'll get into the details later, but the basic thought is this: what if time isn't a flow, but a series of tiny jumps? Imagine watching a slow-motion video. At first, everything looks fluid, but the slower you go, the more you begin to see the frames. Could time be the same? This might sound like science fiction, but in the world of quantum physics, nothing is ever quite what it seems. Now, before we go deeper into that idea, let's slow down for a moment. For you and me, time is memory. But what if all of that memory, rhythm, feeling is just the way we perceive change? And what if time isn't a real thing at all? This isn't just a poetic idea, it's something scientists actually debate. And that brings us to a powerful thought. If time is made of change, what happens when there's no change? Let's imagine the earliest moment in the universe. The very beginning, before stars, before space, before matter. In this strange instant, can we even say time was happening? Or was it just potentially a clock, not yet ticking? These are questions we still don't fully understand. So, what is time, really? Is it a river that flows past us? Or are we the ones moving through a still landscape? In the next chapter, we'll meet the smallest known moment in the universe, the Planck time. But for now, breathe slowly. Let the question rest with you. There's no rush. Time, whatever it is, can wait. Chapter 2. Planck time. The pixel of reality. In our last chapter, we gently asked, what if time isn't continuous? What if it comes in tiny, invisible steps? Tonight, we begin to explore that idea, starting with something known as Planck time, a place where the universe is smaller than an atom, where space, time, energy, and matter are not separate things but parts of the same strange, shifting whole. Now imagine shrinking that clock's resolution over and over until it reaches the very edge of what's physically possible. That final limit, as short as time we could ever measure, is called Planck time. To understand Planck time, we have to step into a place where normal physics no longer works. Let's start with a thought experiment. Imagine a clock so precise it can measure moments 1 trillion times shorter than the blink of an eye. Planck time is about 5.39 times 10 seconds. Let that sink in. That's 0.000.5 seconds with 43 zeros after the decimal point. It's like the frame of the universe's movie, the single, indivisible snapshot. Anything shorter than that, physics doesn't know what to say. Not based on human clocks or calendars, but on the laws of reality itself. It's not just short, it's unimaginably short. So small, in fact, that there's no known way to divide it. But where does this number come from? Just like a digital photo is made up of tiny dots, reality itself might be built from these tiny moments. A series of still images, moving so quickly that our minds mistake them for motion. There may be no such thing as half a Planck time, no hidden motion in between. Just click, and then click again. It wasn't invented randomly. Planck time is based on 3 of nature's most fundamental constants. Time feels smooth. We can split a second into 100 parts, 1,000 parts, 1,000,000 parts, and everything still makes sense. But down at the Planck scale, the rules change. Nothing moves, nothing changes. The universe is still. Then, in the next Planck time, it shifts again. In this model, space and time are not continuous, but made of tiny, finite loops. Like threads woven into a fabric, each loop represents a piece of space or time. There's no such thing as half a thread. The fabric has a structure, a texture, a smallest unit, that in the gaps between ticks, there is nothing, a domain beyond space and matter, where new laws apply, maybe even something that gives birth to time itself. Space itself may not be continuous, energy may not be stable, and time may not flow at all. To test Planck-scale physics directly, we'd need a machine the size of the galaxy. It's where our current theories fall apart and where new ones must begin. The speed of light, that every moment we feel could be one of these invisible clicks, that your thoughts, your memories, your heartbeat all dance to the rhythm of Planck time, a place where things appear and disappear, where probabilities replace certainty, and where the idea of time begins to lose its meaning entirely. Knowing but everything we see, stars, galaxies, even our thoughts are part of this cosmic weave. And time, in this model, is just another part of the pattern. You don't see more detail. You just hit a wall, an edge, the end of resolution. Just sudden flips between different possibilities. Planck's constant, only pulses, only now, and now, and now, again. And Newton's gravitational constant. When you combine these 3, you get a natural unit of time. It's as if the universe is whispering, "This is how fine I go." Now, why does that matter? Because if Planck time is the shortest possible tick of the cosmic clock, then it might be the pixel of time. This challenges how we usually think about time. We imagine it flowing, like water in a stream. But what if it's more like a flip? And if that's true, then what lies between the frames? That's where things get weird. In normal life, we don't notice these limits. Instead, the universe might operate in quantum jumps, tiny, all-or-nothing shifts that happen without warning, no halfway state. And in those moments, the smallest slices of reality, time itself, may pause between ticks. This idea is more than poetic. It's supported by some of the deepest work in theoretical physics. One of the theories exploring this is called loop quantum gravity. If loop quantum gravity is right, then the entire universe is built from these loops. So what happens when we try to go beyond that? When we ask, what's smaller than a Planck time? Physics says, we don't know. It's like trying to zoom in on a photo so far that the pixels disappear. Some scientists believe that nothing meaningful exists below this scale, that nature simply doesn't tick any faster. Others think there's a deeper reality hiding beneath, a kind of but we haven't found a way to peek into that realm yet. Even the most powerful particle colliders on Earth can't reach these scales. The energies are far too high, the distances are far too small. So for now, Planck time remains a boundary, a frontier, not just in size, but in understanding. Still, it's a beautiful idea, to think that time, this vast thing we live inside, might be built from tiny, silent steps. And maybe, while you sleep, your dreams unfold across these tiny moments, one blink of the universe at a time. In the next chapter, we'll go deeper into the quantum world itself. But for now, close your eyes if you'd like. Let the thoughts settle quietly in your mind. There may be no smooth flow. Chapter 3, Quantum Mechanics and the Breaking of Continuity. Let's go deeper now into the quantum world. It's not a place you can visit. You can't walk through it or look at it directly. But everything you see, everything you touch, everything you are, is made of it. The quantum world lives at the smallest scale imaginable. Atoms, electrons, photons, quarks. It's a place where nothing behaves like we expect. A place where rules bend, where particles don't always act like particles, and where time itself starts to feel optional. In classical physics, the kind we use for cars, planets, and footballs, things are predictable. They exist in clouds of probability. You don't know where they rue, only know where they might be. You can't measure both their position and speed perfectly at the same time. That's called the uncertainty principle. And it's not a flaw. It's part of reality. If you know where something is and how fast it's going, you can figure out where it'll be in the future. That's how Newton saw the world. Cause and effect. Clear and logical. Light doesn't just dim gradually, it clicks between levels. Even electrons in atoms don't orbit like planets. They jump between energy states. No sliding, no halfway. Just sudden shifts. In fact, under certain conditions, particles can exist in superpositions not just of position or spin but of causal order. That means two events might happen in different orders, depending on how you look. Imagine if making coffee and pouring milk could happen in either sequence, or both at once. But at the quantum level, that logic breaks down. These experiments show that cause and effect aren't always fixed, that it's a pattern we see at large scales, but that vanishes when we look too close. At the quantum level, time might not have a direction. It might not move forward at all. In this strange world, particles don't have exact positions. Now, what does this have to do with time? From far away, the motion is smooth, flowing forward. If you measure one, you instantly know something about the other. Uncertain, disconnected, timeless. It's as if they share a connection outside of space, and maybe outside of time. But zoom in close down to the water molecules and that smooth motion disappears. The molecules dance randomly, with no clear direction. When you're in pain, time stretches. When you're in love, it disappears. Well, in the quantum world, everything happens in jumps. Energy isn't absorbed. Smoothly it comes in packets. No clock, no flow. These models don't assume time exists at the start. What if time isn't real at all? What if it's not a thing, but a trick? A result of something deeper, something more mysterious hidden beneath the surface of our reality. They try to explain the universe using only states and transition snapshots and changes. No ticking clock, just probabilities shifting from one pattern to another. No past, no future. Maybe it doesn't even exist. Just like energy has the photon, and matter has atoms, time might have its own smallest piece. But deep below, at the quantum level, maybe there is no flow, only change. Sudden, silent, unpredictable change. Maybe it's not the backdrop to everything but something that appears when quantum systems grow large enough. When particles combine into atoms, into matter, into brains, then time feels real, like consciousness, like life, like us. Entangled particles act as if space and time don't limit them. That piece, as we discussed earlier, could be the Planck time, a quiet dance of change, a rhythm with no beat, a mystery that touches every part of our lives, but may not exist in the way we imagine. And if space and energy are quantized, what about time? This kind of behavior is called it's the reason we use the word quantum at all. It means that the universe, at its deepest level, isn't smooth. It's grainy, made of tiny, finite steps. Some physicists believe time might also come in quantidiscrete, indivisible units. But the quantum world does more than hint at small steps. It also challenges the very meaning of before and after. In some quantum experiments, the order of events gets fuzzy. This isn't science fiction. It's been demonstrated in labs using photons and clever setups. There is even a theory that the flow of time, the sense that one moment leads to the next, emerges only when we zoom out. It's like watching a video of waves on the ocean. Maybe time is the same. From where we sit, time seems to flow. Seconds pass, days begin and end, memories fade. Another strange idea in quantum physics is called quantum entanglement. When two particles become entangled, their states are linked no matter how far apart they are. Einstein called this spooky action at a distance, and though it sounds impossible, it's real. We've tested it many times. What does this tell us? Maybe time isn't as fundamental as we think, but before that, before complexity, before measurement, maybe there is no time, just pure quantum behavior. This leads to a fascinating question. What if the passage of time is a story we tell ourselves? Think about it. When you sleep, time fades. When you dream, minutes can feel like hours. When you meditate, time slows. Our experience of time is deeply personal, but in the quantum world, maybe it's not personal at all. Instead, what exists is change. One quantum state flipping into another. Just this moment, and then the next. Some scientists are even trying to build models of physics without time. And in some of these models, time appears only as an illusion, something that becomes useful when looking at systems with many parts. So, where does that leave us? It leaves us in a strange place, a beautiful place, a place where time is no longer a river, but a puzzle. In the next chapter, we'll explore that idea even further. But for now, breathe in. Let this settle like dust in a quiet room. Let the idea of timelessness soften your thoughts, and let yourself rest, even if time itself isn't. Chapter 4. Planck time. The edge of understanding. Imagine a clock. Not the kind you hang on a wall or wear on your wrist. This clock doesn't tick every second, or even every nanosecond. It ticks once, and only once, at the very boundary of time itself. And we can't design an experiment fast enough to capture something that brief. Instead, it's a theoretical construct, a product of our best understanding of physics. When we try to push the boundaries of the very small and the very fast, it's the shortest possible meaningful interval of time. Any attempt to describe what happens within a time frame shorter than that runs into a wall. Physics, as we know it, just doesn't work at those scales. It suggests that between one Planck time and the next, nothing exists. No motion, no change, no reality as we understand it. Only after a Planck unit passes can anything actually happen. If we could understand how time behaves at that scale, we might finally reconcile general relativity. If time is not continuous, and if reality refreshes at Planck intervals, then could we in some way be living inside a kind of programmed reality? Could Planck time be the universe's frame rate? We can't build instruments that operate at those timescales. Remember, behind those familiar seconds and minutes, there's a deeper rhythm, one that ticks not with gears or quartz crystals, but with the very fabric of the universe itself. And within that rhythm, Planck time is the smallest beat, the first tick of everything that ever was, and perhaps the last tick of everything that will ever be. For now, Planck time is like a signpost, marking the limits of our knowledge, a silent whisper that there is more to time than meets the eye. And quantum mechanics, the two great pillars of modern physics that, right now, don't play well together. Others wonder whether Planck time might point to the very structure of spacetime itself. Could space and time be made of tiny building blocks? Could the universe be like a cosmic simulation running on discrete steps? It's like reality is blinking in and out of existence at unimaginable speed, far faster than we could ever notice. Our current theories break down. Space and time stop behaving like smooth, continuous fabrics and begin to shimmer with uncertainty, as if they're made of discrete, vibrating chunks. Time and space themselves were just being born. In those early instants, only Planck time matters. It's the only scale where both gravity and quantum effects play equally strong roles. And because we still don't have a complete theory of quantum gravity, we can't describe what really happened during those Planck moments. It's the point where general relativity and quantum mechanics start to clash, and when that happens, things get weird. That's what scientists call Planck time, the smallest unit of time that still has physical meaning. It's not just small, it's calculated using three of nature's fundamental constants: the speed of light, Planck's constant, and the gravitational constant. When combined in a specific way, they give us a unit of time, about 5.39 times 10 seconds. But why does that matter? Not because they think we're living in the Matrix, but because they know that to truly understand time, we have to explore every possibility, even the strange ones. And the closer we look at Planck time, the more it hints at a deeper structure beneath the surface of reality. It is so small that you'd need 10 of them just to make up one single second. That's a 1 followed by 43 zeros. It's a number so far beyond our everyday experiences that it almost feels unreal. Planck time isn't something we can observe directly. We can't build a clock that precise. To understand Planck time, we have to go back to the formulas that define it, because Planck time represents a limit, a kind of cosmic speed bump. This leads to a fascinating implication. If there is such a limit, then time itself might not be continuous. It might come in tiny packets, indivisible units, much like how matter is made up of atoms. If that's true, then the smooth flow of time we experience might actually be an illusion, much like how a film is made up of individual frames that move fast enough to seem fluid. The idea of time being quantized, broken into pieces, challenges everything we think we know. Now think about the beginning of the universe. Right after the Big Bang, everything was compressed into an unimaginably small and dense point. It's a mystery zone, a window into the unknown. Some scientists believe that cracking the code of Planck time is the key to unlocking a unified theory of everything. And here's where the speculation begins to stretch the imagination. This may sound like science fiction, but physicists take these ideas seriously. But until we develop a full theory of quantum gravity, we can't test these ideas. So the next time you glance at a clock or check the time on your phone, Quantum Time, Chapter 5, Entanglement and the Flow of Time, let us take a quiet breath and follow a thread that puzzled scientists and philosophers for decades: quantum entanglement. Imagine two particles so deeply connected that even if you separate them by galaxies, changing one instantly changes the other. It sounds like magic, but it's real. Einstein famously called it spooky action at a distance. But what does this have to do with time? To answer that, let's take a step back and look at how we usually understand the flow of time. You could measure one and instantly know something about the other. Some researchers have explored whether particles can be entangled not just across space, but across different moments in time. That would mean a particle now could be linked to a version of itself in the future or the past. At the other end is a moment in your future. Most of the time, we see the string stretched in a line. But what if the string is tangled? Instead, it might arise from something deeper, like patterns of entanglement. In other words, time could be something that shows up only when particles start interacting in complex ways. Below that, time might not exist at all. What if the middle loops around and touches both ends? But even if we don't fully understand them, they point to something beautiful. Time might not be what we thought. The flow of time might not be a simple line. It might be a dance, full of loops and twists, bound together by invisible connections we're only beginning to understand. It might not be a ticking clock, or a straight road from birth to death. It might be something much more subtle, more flexible, more alive. Because no matter how quantum or strange the universe becomes, we still feel the seconds slip by. The question is, what will we do with them? In that case, the past, present, and future could influence one another in subtle ways. This might be closer to how time works in the quantum world. In fact, Certain quantum experiments have hinted at this, suggesting that choices we make now could influence outcomes that seem to come before the decision. In some experiments, it seems like event A causes event B, and B also causes A. It's like both events are part of a single, unified structure. Below that, we don't even know if before and after make sense. In that realm, particles exist in a haze of probabilities, waiting to become something definite. It's as if the universe is constantly deciding which path to take, and that choice made again and again at every moment is what gives us the feeling of time passing. That's hard to wrap your head around. But in the quantum world, it makes sense. Time doesn't have to follow a single direction. That means the fabric of the universe, space and time included, might come from the connections between particles, not the particles themselves. It's like reality is woven from invisible threads, and those threads are what create the feeling of time moving forward. Instead, it might depend on how you observe it. It's like the arrow of time is being twisted into a loop, but that shared state doesn't seem to be traveling through space. It's just ... there. Some physicists think that entanglement might mean everything is more connected than we think, not just in space, but in time too. We experience it as a one-way river, past, present, future, Kaleidso effect. You wake up, you stretch, you pour your coffee. If entanglement reaches across time, the future and the past could be part of one continuous whole. That doesn't mean we're time traveling in the sci-fi sense, but it does suggest that time might be less like a river and more like a web, everything connected, not just from left to right, but up and down, forward and back. One thing happens after another. Time feels smooth, unbroken, always moving forward. But in the quantum world, time doesn't always behave the way we expect. With entanglement, you can have two particles separated by light years that seem to affect each other instantly faster than light. This breaks the rule of cause and effect, at least how we know it. It makes us question whether time flows the same way at the quantum level. Here's the thing. When two particles become entangled, they share a state. Could time itself be entangled? It's a strange question, but one worth asking. This idea challenges one of our deepest beliefs that time only moves forward. Let's imagine you're holding a string. At one end is a moment in your past, say, your childhood. Now, some scientists are exploring the idea of quantum causality, a kind of fuzzy cause and effect where the order of events isn't always clear. One fascinating possibility is that time is an emergent property. It might not be a basic ingredient of the universe. That brings us back to the idea of the Planck timed, the smallest unit of time that has meaning. And here is something even more curious. Some physicists believe that spacetime itself might be built from entanglement. It's easy to get lost in the strange ideas here. So the next time you feel the passing of time, the ticking of a clock, the sun rising and setting, remember that underneath it all, something much stranger might be at play. In the final chapter, we'll explore what all of this means for us, not just as curious minds, but as humans living inside time. Chapter 6. Why the smallest time still matters. So now we've come full circle from the vast, unknowable beginnings of time, all the way down to the tiniest fraction that could ever possibly exist, the Planck time. But here is a question that might be floating in your mind. If we can divide time any smaller, and if it only truly matters at the edges of black holes or in the first moments of the universe, why should we care? Why does quantum time matter to us ordinary people, living ordinary lives, who will never fall into a black hole or build a particle accelerator in our garage? Here's the quiet truth. The smallest parts of nature shape everything above them, that no matter how vast and chaotic the cosmos might seem, there's a rhythm beneath it. If time began with a big bang, did something exist before that? Because if Planck time marks the beginning of time as we know it, then maybe understanding it better could give us a peek behind the curtain. But under it all, beneath your perception, lies a scaffold of Planck moments. Too fast to measure, too small to see, yet they're there, stacking one upon another, creating what we call now. Maybe the edge of time is not a wall, but a window. If you want more calm stories about strange truths and hidden worlds, subscribe to the channel. And if there's a question or thought keeping you up at night, share it in the comments. You never know, your question might be the beginning of our next story. To sit with a mystery, to listen deeply, and maybe, just maybe, you felt something shift, even for a moment. Or is before even a valid question? Some physicists argue that asking what came before the Big Bang is like asking what is north of the North Pole. how we try to touch the edges of reality using only thought, silence, and the smallest numbers we've ever imagined. And if that sparked a question in your mind, you're not alone. That curiosity is what drives science, and wonder, and our shared need to understand where we came from. It's a meaningless question, because time itself didn't exist. It may not sound like anything you've heard, but it's ticking, gently, just beneath reality. And every tick is a whisper from the very beginning of time, a note in a song older than everything we know. But others aren't so sure. They believe the quantum formed the seething soup of probabilities and potentialities might hint at a universe beyond ours, maybe even a multiverse, or just leave emoji. We'll know what it means. A tiny beat, a quiet clock. It doesn't tick like the ones on our walls. It doesn't count like the ones on our phones. But it's always there, in the background, holding the rules together. That's Planck time. It's not something you can hear or see, but it's the frame everything else is built on. Even if we never touch them directly, they are the foundation of what is. Every breath you take, every moment you experience, is built on layers of reality that we're only beginning to understand. There's the idea that time, at its most basic level, might not be smooth or continuous. Instead, it could be made of discrete moments, like frames in a film. Between each Planck second, nothing happens in the way we understand. It's like the universe is ticking along in silence, only revealing itself one flash at a time. That's not just a philosophical idea, it's something real scientists are trying to test. And if they ever do prove it, our entire understanding of cause and effect, of motion, of life itself, might have to be rewritten. And Planck time, it's not just a number, it's a signpost, a marker that says, beyond this, something very different begins. When physicists talk about quantum gravity or the search for a theory of everything, what they're really trying to do is make peace between the rules of the very big and the very small. Time is the battlefield where that struggle plays out, because general relativity tells us that time bends and stretches, and quantum physics says it jumps and fluctuates. Both are right, but they're speaking different languages, and until we understand how time works at the smallest possible scale, we can't translate between them. Some theories go even further, but there's something oddly comforting about this, isn't there? This also opens up a bigger mystery. What happened before the first tick of Planck time? Here, again, the smallest unit of time becomes a doorway to the biggest questions we can imagine. And so we return to the present moment. You're here now, breathing, blinking, thinking. Time is passing second by second, unnoticed. So the next time you stare at the stars, or listen to silence, or close your eyes before sleep, remember this: the universe has its own heartbeat. You've just taken a journey into the smallest slice of time imaginable, and maybe into the nature of time itself. If you enjoyed this quiet dive into the quantum, consider liking this video. Sleep well, traveler. If you've made it this far, thank you. In a world that moves faster than ever, you chose to slow down. This video wasn't just about quantum time, it was about how we measured the immeasurable. If that resonated with you, if you felt a sense of stillness, wonder, or just wanted a quiet space to think, this channel was made for you, please consider liking this video. Not just because it helps us grow, but because it helps others find this kind of content, gentle, thoughtful, and a little bit different. Subscribe if you'd like more stories like this about deep time, cosmic riddles, or the strange poetry of the universe. And if you're still awake, tell us in the comments what moment in the video stayed with you. This is Echoes from Tomorrow, and we're just getting started.